Okay, so I wanted to go over problem number 42, and I'm going to show you how you might work with this in the general approach to nodal analysis and also in the format approach. And the format approach later, that will look a lot like your number 43 as well. So hopefully this will help you to be able to set up your equations for nodal analysis. So remember, for nodal analysis, we have to identify, first of all, the nodes that we have in our circuit. So for instance, we have a node here at the bottom. That is our reference node where we assume V is equal to 0. And then we have a node up here on the top left, and I'm going to call that VA. So we know that that is all at the same voltage, but we don't know what that voltage is. So I'm going to name it VA. Then on the right-hand side, we've got another node over here, and that is VB. Again, we don't know what that voltage is yet, but we know that all the points in that box that I'm showing you here have to be at the same voltage. So we're going to call that VB, whatever that is. And what we're going to do is for each node, aside from the reference node, so we don't really need the reference node down here, but for the other two nodes, we're going to write Kirchhoff's current law equations where we assume that all the currents are leaving the node. For instance, for VA, we're assuming those three currents are leaving the node. So let's look at that equation for VA. So in the general approach, we're just going to describe each individual current. So for the 12 ohm resistor, the voltage on the top of that resistor is VA. The voltage on the bottom of the resistor is 0 because that's our reference node. So VA minus 0 divided by 12 would be that current. So I'm just going to say VA over 12 is the current leaving the node through the 12 ohm resistor. And then I come next to the 12 amp source, and the 12 amp source is already leaving the node, and it is a constant of 12 amps, so I don't have to do any math there. I'm just going to add my 12 there. And then the tricky one is on the top here, so through the 9 ohm resistor. So if my current is leaving the VA node and going toward the VB node, then the voltage drop is going from VA to the other side of the 9 ohm resistor. So that voltage drop, and I'm going to say plus because, again, we're assuming all of our currents are leaving the node and we're just going to add them. That would be VA minus whatever the voltage is on the other side of the 9 ohm resistor, so right here. Okay, so at that point, what would the voltage be right there? Well, it's not VB because we have this 54 volt source between VB and the 9 ohm resistor. So what it would be is whatever VB is plus the 54 volts. Okay, so VB plus 54 is the voltage on the other side of the 9 ohm resistor, and when we divide by 9, that would equal 0. Okay, so there's our first equation, and if you want to rearrange it a little bit, this is 1/12 times VA. Let me do that a little bit differently here. 1/12 VA plus 12 plus, and then I'm going to separate out the VA and the VB and the 54 over here. 1/9 VA minus 1/9 VB minus 54 over 9 equals 0. And then when you put your VA terms together, you have 1/12 plus 1/9 VA minus 1/9 VB. And then I'm going to move the 12 to the other side, and it becomes negative. I'm going to move the 54 over 9 to the other side, and it becomes positive because it's negative up here in the equation, and which that would be, of course, -6. All right, so there is your first equation. Again, we're always trying to put the VA term first, VB term second, and then our constant on the right side of the equal sign. Okay, let's look at our VB now. So for VB, again, we're assuming all of our currents are leaving the VB node. So through the 5 ohm resistor, we're assuming we have a current going this way down through the 5 ohm to ground, and through the 20 ohm resistor down as well. And then through that 9 ohm resistor at the top, the current's going that way. Now, don't let it concern you that we're looking at the current through the 9 ohm resistor going to the left here, whereas we were looking at it going to the right from the VA perspective. That's just how nodal analysis works. We're just going to make that assumption that all of our currents are leaving, and we will allow the math to tell us later what is really going on. Okay, so for VB, for the 5 ohm resistor, the current going down through there, again, this is an Ohm's law relationship. It's whatever that voltage drop is across the resistor divided by the resistance. So VB minus 0, change that. So VB minus 0 over 5. So VB over 5. I think I switched to the wrong color. Okay, and then for the 20 ohm resistor, again, it's VB minus 0 over 20. And then here comes the difficult part again. We've got that 54 volt source. So what is the voltage drop across the 9 ohm resistor? If we start here at VB, it's going to be VB plus 54 is the voltage right here, VB plus 24, plus 54, sorry. And then on the other side, it's VA. So we're going to subtract the VA. So that's going to be the difference in voltage across the 9 ohm resistor. We set that equal to 0. Those are the only 3 currents we have. Again, we can do some math to get our terms together. So 1/5 VB plus 1/20 VB plus 1/9 times VB plus 54 over 9 minus 1/9 times VA. And again, now we want to get our VA term at the front here. So there's our VA. And then our VB term, we've got 1/5 plus 1/20 plus 1 over 9 VB. And then our 54 over 9 is 6. When I move that to the other side, it'll become a negative 6. And there's your second equation. At this point, you can put this into your matrix and solve. And I'll give you those numbers in just a minute so you can look at that. So next, let's look at how we might apply the format approach to this same circuit. So here, with the format approach, we're really looking for current sources. That's going to help us the most in our work here. So what we want to do is take this voltage source, the 54 volt source, and series with the 9 ohm resistor, and we want to convert that to a current source. So you know how to do that. We have, we're just going to remove that 9 ohm resistor and the 54 volt source. And we're going to convert that to its equivalent current source. So you did this in the last week, so this shouldn't be new for you. That 9 ohms is going to become a parallel resistor. Our current source is going to point in the same direction as our positive terminal of our voltage source. And its amount is going to be the 54 volts divided by 9, or 6 amps. So what we're going to do is remove the voltage source and replace it with the current source. So I'm going to redraw my circuit here. Got our 12 amps there. And here we're going to have the 9 ohm resistor. And the 6 amp source now. And here I've got my 20 ohms and my 5 ohms. Okay, so now that we have only current sources in the circuit, there's 12 there, now we can start looking at our nodal analysis. So again, we're going to start the same way we did before with finding all of our nodes and labeling them. So we do have this node here at the bottom where all these wires are coming together. That's going to be our reference node, where V equals 0. Now up at the top right, top left, we have this node here, just like we did before. It's not a different node. We do have, instead of only one path coming to the 9 ohm resistor, we now have 2 paths, 9 ohm resistor and the 6 amp source. So that's just going to increase the number of paths we have for our currents there. And then on the right-hand side, we have another node here. Again, when you think of a node, think of a spot in the circuit where you have multiple wires coming together and they all have the same voltage. So if I somehow had a resistor inside one of these boxes, the VA box or the VB box, that would change the voltage. And so those would not be part of the same node anymore. So just be really careful about how you choose your nodes. And now let's talk about writing our equation. So for format approach, we know we're going to have a VA column and a VB column and a constant column on the right of our equal sign. So what we're going to do for the first equation, and that's the VA equation right here, we're going to add together all of the conductances that are connected to VA. And by conductance, I mean the inverse of the resistance. So we've got a resistor of 12 ohms here and a resistor of 9 ohms here. So that would be 1 over 12 plus 1 over 9. Those are the conductances connected to VA. And that's our VA term. For VB, we're going to subtract any conductances connected to VB as well as VA. And that's just this 9 ohm resistor up here that's connected to both. So that is going to be minus 1/9 times VB. And then on the right-hand side, this is where our we're going to have our current sources. So this is why we converted our 54-volt voltage source to a current source. So we've got 6 amps here, and we've got 12 ohms here. So in this case, for the format approach, we're actually going to add any currents that are coming into the node, which would be the 6 amps, and we're going to subtract any currents that are going out from the node. That is the 12 amp source. And there's our equation. So 1/12 plus 1/9 VA minus 1/9 VB equals -6 amps. Tell you what, let me get rid of the units there. That might be a little bit confusing. Plus 6 minus 12. And if we go back up to here, you see that that's really the same equation that we had here anyway, just a bit quicker to get the equation using the format approach. Now let's look at VB. So my second equation is going to be looking at those branches from the VB perspective. So for the VB term, I'm going to start with my VB term because that's the node that I'm looking at right now. I'm going to sum all the conductances connected to that node. So there I've got the 9 ohm resistor again, and the 20 and the 5. So that's going to be 1 over 9 plus 1 over 20 plus 1 over 5. And then the VA term, and that's plus because that's the node that we're looking at right now. And then I'm going to subtract the conductances connected to VA, which again is just that 9 ohm resistor. So that's going to be a minus 1/9 VA. And then on the right, I'm going to add any current coming into the node and subtract any currents leaving. And that 6 amps is now leaving the VB node. It was coming in for the other, and it's leaving for the VB node. So when you plug this into your matrix, so this will be your column 1, your column 2, and your column 3. When you plug that in, you should get, let me see, where's your VA? VA should be a negative 48.96 volts. VB should be negative 31.68 volts. So notice that what that's going to mean, and I'm going to go ahead and show you up here in the original circuit. So if you have a voltage at A of negative 48.96 volts up here, and you have a voltage at VB of 31.68 here, what that tells you is the voltage at B is higher than the voltage at A, so you are going to see this current up here going this way. The current coming from the V equals 0 node or the ground node actually be going up this way because, again, you're going from 0 to a negative almost 50 volts. Same thing with your 5 ohms and your 20. So you'll see these two going in and this current leaving the VB node, and then 12 amps this way, and then, of course, through the 12. So when you do your calculations at the end, figuring out what your currents are, you should see all of those directions line up for you as well. Hopefully that helps. And this problem right here is very much like your number 43. So hopefully that'll help you with setting up the equations for 43 as well.